This is a little bonus problem that I put on a physics quiz right at the beginning of first semester mechanics, where we're talking about a little bit of vector mathematics. So I was kind of playing with an idea when I was writing the quiz and just came up with this funny little theorem. So it says, show that if two vectors v and w have the same length, then v minus w must be perpendicular to the vector v plus w. Now my intent here was to just get a pure symbolic algebraic solution, but it also turns out the geometric interpretation of it is interesting, and it might be familiar to some of you from high school geometry. So we had talked in class about properties of the dot product, like it's distributive and commutative, and my intent here is that to show these two vectors are perpendicular, you would simply take their dot product. So we take the vector v minus w and dot it into the vector v plus w. And again, we had already talked about the fact that the dot product is distributive, which means we can repeatedly distribute and get basically something like FOIL out of this. That's going to look like v dot v for the first term, plus a v dot w for the second term, minus a w dot v for the third term, and minus a w dot w for the fourth term. Now we also discussed that if you dot a vector into itself, you just get the square of the magnitude of that vector. So v dot v is actually just v squared. Again, in physics, if we show just the symbol v, that means the length of the vector v. So it's a very simple notation. Now for these cross terms, I'm going to get a little bit of work done at the same time. Remember, the dot product is commutative, which means v dot w and w dot v are the same thing. So I'm going to leave the first one alone and just call that v dot w. But the second one, I'm going to turn it around. So we're exploiting the commutativity of the dot product right now. I'm going to call that v dot w as well. And then at the end here, w dotted into itself, that's the magnitude of w squared. So I notice that my cross terms are going to cancel out. I have a v dot w minus v dot w, and those are gone. And I'm left with just v squared minus w squared. But from the very beginning, we were told this only works if the vectors have the same length. So v squared minus w squared is 0. So now let's take a look at the geometric interpretation of this thing. Here's a vector v, and now a vector w that I tried to make approximately the same length in the picture. I know it's not perfect, but basically the same length. And so if we look at v plus w, we're going to find that by adding those two vectors head to tail. And I decided to make another copy of w, so we can see w plus v is the same thing as v plus w. But more importantly, the thing we've built here is called a rhombus. So that's a parallelogram where all the sides are equal in length. Let's get a picture of v plus w into the diagram. That goes from the tail of the first vector to the head of the second. And there's its name, v plus w. Now remember, v minus w, that's a vector pointing from the head of w to the head of v, provided their tails are in the same place, which they are. So there's v minus w. And what we notice here is that the intersection of v minus w and v plus w appears to be happening at right angles. So I just wanted to take a look at this geometric interpretation because it is something that comes up in high school geometry. I personally don't remember much from high school geometry, but some of you might. As it turns out, the diagonals of a rhombus intersect at right angles, and that's something you may have proven at some point. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.